So, we used minimum potential principle for getting the eigenvalue problem for buckling, and then we got the Rayleigh quotient also and noted the property of Rayleigh quotient. Rayleigh quotient has a minimum locally whenever the W, the function that we take, becomes the buckling mode shape. Okay. So, by minimizing Rayleigh quotient for column buckling, we get the fundamental buckling mode shape, buckling value, buckling load. Okay. So, that is what we are taking now. If we want to design the strongest column for given amount of material. Okay. Strongest column for different amount of material, that is, I would say subject to the volume constraint A dx 0 to L minus V star less than or equal, like we had done for the bars and beams before. We are doing it for the column. What do I mean by that? We have a column. I will only draw the neutral axis now. Okay. Let us say fixed free column, boundary conditions do not matter. Now, instead of taking uniform cross section, we will take a variable cross section. Okay. A variable cross section. Okay. Everywhere the cross section, this A of x is a function of x. Again, our x goes here in this direction, x equal to 0 and x equal to L here. We want to find this function A of x. That is why that is became our design variable. Okay. But how do I get P critical? That is where we use a Rayleigh quotient. So, what we do is we rewrite this problem, maximize A of x. Okay. P critical, we know that if I minimize Rayleigh quotient with respect to Wx, that is what is the Rayleigh quotient. If you recall from the last lecture, this was the Rayleigh quotient for column buckling, okay, the W. So, we minimize P with respect to W, then we get the buckling load, fundamental buckling load. So, I can say that Rayleigh quotient, I will write 0 to L E I W double prime square dx divided by 0 to L W double prime W prime square dx. Okay. Where is A here? We had already discussed, that is actually in I. We had noted that I can be written as alpha some number A raised to beta. Okay. So, it depends on the cross section shape. If it is a rectangular cross section, we had already discussed that if I have a rectangular cross section with breadth B and depth D, this kind of a cross section, then I, as we know, is B d cube by 12. So, since BD is area, I will take D square out and then call this BD, which is area. Okay. This is area. So, my beta here is equal to 1 and this becomes alpha if I assume the depth of the beam. Okay. That is where the area of cross section want to come. So, we will replace that in this case with alpha into A, because beta is equal to 1, and what is alpha? Alpha is D square by 12. Okay. And then we have the volume constraint subject to volume constraint 0 to L A dx minus V star less than or equal to 0. Okay. So, we have the problem statement now. Okay. The first thing we do is to write the Lagrangian for this problem. Lagrangian, we have E I W double prime square dx. Okay, let me change, instead of writing as I, we will write it as E alpha A, that is E I W double prime square dx 0 to L divided by 0 to L W prime square dx, that is the objective function, plus we will have lambda times 0 to L a dx minus v star. Okay. When you have this, we have to take variation. Next step, we have to take variation of Lagrangian with respect to A, that gives us design equation to design the area of cross section. Likewise, when you take this with respect to W, you get in this case the eigenvalue problem itself, because the P critical, when we solve the W, if you take the minimization, you get the buckling equation, buckling governing equation. Okay, because we did not write the governing equation separate one, we parceled it into the objective function like that, minimization. That will give you the P critical, minimum value of that, corresponding W is going to be our buckling mode shape. So, we get buckling governing equation. Okay, and then we have the volume considered less than or equal to, complementarity condition and all of that. Okay. So, let us first do this part, variation of Lagrange with respect to A. So, A here is in the numerator only. So, you would do that, denominator just stays the way it is. Okay. So, that gives us 0 to L E alpha W double prime square. We can either do that, just directly write Euler-Lagrange equation for it, okay, because this is just a constant in the denominator, let it be there, we will have the rest. Okay. So, if we do this, we get E alpha A is there. So, W double prime square minus lambda, that comes from here, except this will be divided by 0 to L W prime square dx, that this is actually plus, okay, that will be equal to 0. That is what we get when you take variation with respect to A. So, the buckling equation, if you take, then we have to take variation with respect to W here, that is there W prime and W double prime. We have to use this quotient rule of differentiation when you do this. This is a functional, that what we have here is ratio of two integrals is also a functional, we can take that. Okay. So, first we write 0 to L W prime square dx over here into the variation of the first part, okay, that will be E alpha W double prime, E alpha A also will be there, E alpha A W double prime, since double prime there will be double prime also, right, d square by dx square, that we will have for the numerator, then minus this will be there 0 to L E alpha A, okay, W double prime square here, okay, and then denominator we do not have A. Okay. So, we have to make one little change, okay, that is actually important, we missed it. So, when we derived this Rayleigh quotient over here, we assumed uniform cross section. If we do not assume uniform cross section right here, when you do all this, if potential energy, that is correct, if we write this as I and alpha, we write alpha A raised to beta or whatever, when we are taking these derivatives, we assume that especially here that I will come, we would not have gotten just this here, this I also would have gotten double prime, okay, this also would have got double prime because it is inside, right. That will change a few things over here, okay, when we write everything, all that would have changed, A double prime and so forth. So, we have to redo the Rayleigh quotient here in order to get it right. Otherwise, what is happening for us here is that we are seeing that there is no A here in the denominator, okay, and these other things are missing. So, to redo the Rayleigh quotient. When we do that, we put the problem like this, then we get the design equation if we do it properly, and then buckling equation here, and then we will have the complementarity condition that lambda times this constraint a dx minus v star equal to 0, and then lambda greater than equal to 0. Okay. This one will have to redo it, and then I suggest that you do all this after rederiving the Rayleigh quotient here, assuming that I, second moment of area, actually varies with x. Okay. Then we will get this Rayleigh quotient properly, and then we can do what we intend to do. If we just do it like this, there will be a problem, because we assume that area of cross section is constant and this, but now we are talking about that being variable. So, we have to rederive that equation. That is easy enough. It is just that in these steps that we took, we should not forget that over here I is varying. So, there will be two terms coming. So, over here we will have E I prime W double prime, okay, plus there will be two terms, right. So, when we do this, two derivatives we have to do over there. So, E I prime W double prime, and then E I W triple prime, and one more prime will be there, because this is d square by dx square. So, that will again give us E I double prime W double prime, okay, and then E I prime triple prime. This will have, now we have done it for this, when I do it for this, another one of this will come, that will become 2, and then I will have E I W fourth prime. That is what we get over here for the buckling problem. Okay. And after that, when we do this by multiplying by W, each one of them we have to reduce all that. So, now the Rayleigh quotient actually becomes different from what we have, because we have to do integration by parts for this and this and this. We have done only for this now, because that was there, but these two terms were not there, because we assumed that I is constant. So, I prime and I double prime are not there. Okay. So, now when you put them back and do this integration by parts, you will get a Rayleigh quotient, then that will have dependence on I as well in evaluating the Rayleigh quotient. Then you will get the correct value over here for columns that have variable cross section, where this is more here, less here, and then becomes more or less, and so forth. As it is changing, we get for that. Okay. That is what we can do when you solve this problem using what we call the optimality criteria method. Optimality criteria method, we can get the solution for this optimal column or strongest column for given amount of material V star. Okay. That is how this works. Remember that we have here a max min problem. Okay. That is, we are designing, that is by varying A of x, and we are minimizing to get the governing equation. That can be done for a general elastic structure also, not just for column buckling problem. Any structure we can do this minimization of potential energy with respect to, let us say, state variable for a beam, column, whatever, minimize the potential energy, that happens to be equal to negative of the strain energy, okay, at equilibrium. So, we can say we can maximize negative of strain energy with respect to A of x. This problem, max min problem, is equivalent to minimizing strain energy with respect to A of x subject to, okay, this also needs to have the volume constraint, that does not go away, subject to volume constraint 0 to L A dx less than or equal to V star. Okay. This is subject to the same thing 0 to L A dx minus V star as we normally write less than or equal to 0. But here we have to write, if it is a beam problem, we have to write, because the strain energy for a beam, if I take 0 to L half E I W double prime square dx. So, I have to put a governing equation E I W double prime there is a loading Q equal to 0. Okay. So, instead of posing the problem with the objective function and the constraint, which is the governing equation, this constraint is a governing equation. Okay. Instead of doing that, we can put it as one maximum problem. In order to see where it comes from, we have to discuss what is called Clapeyron's theorem. Clapeyron's theorem, which is quite simple. That is, if I were to take the potential energy, okay, remember that here this is strain energy, here it is potential energy. How are we doing this? Instead of putting the objective function and the governing equation, we can get away with one maximum problem, like we are doing for the column. Column, again why are we discussing this? Because we pose this as a max min problem, okay, with the Rayleigh quotient. That can be done in general for structural optimization. Okay. So, Clapeyron's theorem, where we have potential energy, let us take it for a beam 0 to L half E I W double prime square minus, there is a loading Q minus W dx. There is a work potential, negative are the work done by external forces. Now, when we take the variation of potential energy with respect to W, that gives us the equilibrium equation, right, or variation if I do. So, we write 0 to L E I, let me write I properly, E I W double prime delta double prime, okay, minus Q delta W dx equal to 0. This we said is a principle of virtual work. Okay. So, now if you look at this problem here, this delta W is our variation, is arbitrary. Okay, that is like virtual displacement. Okay, this is the statement of principle of virtual work. This portion is internal virtual work, this is internal virtual work, this is external virtual work. Okay. So, again what is IVW? That is internal virtual work, EVW is external virtual work. Both being equal is the principle of virtual work. So, IVW is equal to EVW, which we had discussed earlier, is the principle of virtual work, or as we call the weak form of the governing equation. That is what this is also called, the weak form and principle of virtual work, PVW, and principle of virtual work. Okay. Note that delta W is arbitrary. When it is arbitrary, let us say at equilibrium this must be true, let us take it as W itself. Okay. When we do that, what this gives us is 0 to L E I W double prime, delta W prime is W double prime, so that becomes square, dx is equal to 0 to L q into delta w dx. Okay. Now, if you see what is potential energy here, so we can take this as put half and half. I will take half of this to the other side, okay, and bring this over here, okay, only half goes there. So, half will be left behind here, 0 to L E I w double prime square by 2, half is left behind, other half I will take it there, that becomes 0 to L E I w double prime square by 2 dx. Okay. Half I have taken the right hand side, half I have left behind dx, and this one I am bringing back here. So, that becomes minus 0 to L q w dx. Okay. Now, if you look back and see what this is, what we have here is potential energy. That is our definition of potential energy. Strain energy, this is actually strain energy, and this is including the negative sign is work potential. These two added up becomes our potential energy. What is on the right hand side? Minus strain energy. Okay. So, potential energy is equal to minus strain energy, okay, is the Clarence theorem at equilibrium, not everywhere, at equilibrium. Okay. And because of that, when we want to minimize strain energy, we are maximizing potential energy with respect to A of x, minimize energy with respect to A of x, maximizing potential energy with respect to A of x, and minimizing potential energy gives us the governing equation. So, this max min formulation helps us solve problems, and that is how we can do the strongest column problem by doing it as this max min problem over here. Okay. So, this can be numerically done using the so called optimality criteria method. All right. So, we will look at a program in the next lecture as to how the strongest column thing works. Thank you.